Still looking at the superposition approach, our differential equation is y double prime minus 16y equals 2e to the 4x. And what we're going to do is set ourselves up for a possible failure. It's really easy to do. All you do is you neglect finding the complementary function first. So we see here that g of x is equal to 2e to the 4x, which is going to give us y sub p of ae to the 4x. Remember, this is wrong to do. We should always start with the auxiliary function, but I'm going to show you here why. Since we have yp equals ae to the 4x, we get that yp prime is 4ae to the 4x, and yp double prime is equal to 16ae to the 4x. Plugging that into the differential equation the way we just been doing, 16ae to the 4x minus 16ae to the 4x is equal to 2e to the 4x, but no, it's not, because the left-hand side is equal to 0. What happened? This is a case of the right-hand side, the forcing or the input function, e to the 4x, neglected to, the e to the 4x, is actually one of the solutions of the homogeneous differential equation. And so plugging it into the left-hand side is going to give us 0. This is not a way to find a. This is why the first step is to find the auxiliary equation m squared minus 16 is equal to 0, which then gives us that m is equal to plus or minus 4. And so the complementary function y sub c is equal to c1e to the 4x plus c2e to the negative 4x. Now we have a situation where the complementary function shares a term with what we see on the right-hand side of the non-homogeneous differential equation. I'm going to say that's redundant. So we have a redundancy here if we use yp equals ae to the 4x. To avoid the redundancy, we're going to use y sub p is equal to ax e to the 4x. It turns out, to avoid redundancy when you have it, only when you have it, we multiply by the lowest power of x that clears all redundancies. So now we have our form yp equals ae to the 4x, and I'd like you to pause the video and finish this problem. Find what a is and then form the general solution. The derivative of yp is a plus 4ax times e to the 4x. And then yp double prime is 8a plus 16ax, all of that times e to the 4x. Putting that into our original differential equation gives us 8a plus 16ax times e to the 4x minus 16a e to the 4x is equal to 2e to the 4x. We can see that all the x terms on the left add up to 0. They should, because there's no x term on the right-hand side. And since 8a is equal to 2, we get that a is equal to 1/4. So putting this together, we get that y is equal to, remember, it is yc plus yp. And we already found yc, if I remember right, it's c1e to the 4x plus c2e to the negative 4x. And then the form of solution for yp was ax e to the 4x. So since a is 1/4, that's 1/4 x e to the 4x. Now I'd turn you loose to do this next one on your own, but it's got a little bit of a wrinkle that isn't immediately obvious. First off, we've got 4y double prime minus 4y prime minus 3y equals the cosine of 2x. The auxiliary equation 4m squared minus 4m minus 3 equals 0 is going to give us that m is equal to negative 1/2 or 3/2, and so we have a complementary function y sub c is equal to c1e to the negative 1/2 x plus c2e to the 3/2 x. Let's just get that out of the way. We can see that there's no redundancy or overlap between the complementary function and the input function of cosine of 2x. Now here's the thing, folks. we're going to write down y sub p. And if we saw cosine 2x, we might think, well, it's a times the cosine of 2x. And that's almost correct. But our differential equation has the second derivative, the first derivative, and the function itself. When we differentiate a cosine, we get a sine. And so when we see a cosine or a sine in the input function on the right, the particular solution or the form of the particular solution needs to have both a sine and a cosine. We can't assume that they are the same coefficients for the sine and cosine, so y sub p is equal to a cosine of 2x plus b times the sine of 2x. Just know, when you see a cosine or a sine on the right-hand side, your particular solution has a cosine and a sine. Now with that, I'm going to turn you loose. Go ahead and pause this, find the general solution, and then come back. Did you really pause it and do the work? Sometimes I wonder that. Anyway, yp is a cosine 2x plus b sine 2x. Yp prime is then negative 2a sine 2x plus 2b cosine 2x. Yp double prime, negative 4a cosine 2x minus 4b sine of 2x. Putting that into the differential equation, 4y double prime gives us coefficients of negative 16 and negative 16. Sine or cosine first and then sine. Negative 4y prime is going to give us coefficients of 8a for the sine and negative 8b for the cosine. Don't forget, we're distributing a negative 4. A lot of people will remember the 4, they lose the negative, or they just lose the 4 entirely. Negative 3y gives us coefficients negative 3a on cosine 2x and negative 3b on sine 2x. And the right-hand side, of course, was the cosine of 2x. That's how we got into this mess. For this equation now, equating the cosine terms gives us negative 16a minus 8b minus 3a, and then on the right-hand side, the cosine term has a coefficient of 1. So that equation, negative 16a minus 8b minus 3a is equal to 1. Equating all the coefficients on the sine terms gives us negative 16b plus 8a minus 3b equals 0 because there was no sine term to begin with. Solving that system of equations is going to give us a equals negative 19 over 425 and b equals negative 8 over 425. So y is equal to, again, yc plus yp. c1e to the negative 1/2 x also can be written as negative x over 2, take your pick, plus c2e to the 3/2 x, or 3x over 2, minus the 19 over 425 is a, and we had originally put a with the cosine term, so that's going to be cosine of 2x minus 8 over 425 sine of 2x. So we picked up a surprise sine function, and if you check the solution here, you're going to find that it works, and you're also going to find that that sine was necessary. As you may be seeing here, having the correct form for your y sub p when you start all this is really essential. And so that's what we're going to look at now. Assuming there's no redundancy, if our forcing function g of x is 3x plus 2, we have a form for y sub p. Here's what I'll do. We have various input functions or forcing functions. 3x squared plus 2, 7e to the 4x, 8x squared e to the 2x, 3 sine of 2x, and x cosine of 3x. And what I'd like you to do is, using the information that I've given you, write down what you think is the form for y sub p for each of these input functions, and then come back and see how well you did. 3x squared plus 2 is a second degree polynomial, so our y sub p form is ax squared plus bx plus c. 7e to the 4x, just straight exponential, so ae to the 4x. Make sure that those exponents match. 8x squared e to the 2x is the product of a second degree polynomial and an exponential. So yp is the quantity ax squared plus bx plus c times e to the 2x. Again, making sure that the exponents match there. For 3 sine 2x, we have a sine 2x plus b cosine 2x. It doesn't matter the order in which we write them. It doesn't matter which one gets the a and which one gets the b. You're going to solve for those numbers and actually put numbers in when you form your solution. Finally, x times the cosine of 3x is a linear times a cosine. So I need two linears, ax plus b times cosine 3x plus cx plus d times the sine of 3x. The linear, remember, it comes with like a constant, right? Ax plus b, just like a second degree polynomial comes with ax squared plus bx plus c, right? Some people will forget that b or that d in there. And then another thing people do is they might neglect that we can't assume the ax plus b for the cosine 3x has the same coefficients for the sine 3x, and that's why we have cx plus d. We got to account for the likelihood, and it's a pretty strong likelihood, that those constants are not the same values. Now, it would be a pretty bad day if you were working a problem, say this 8x squared e to the 2x, if there's like redundancy. I mean, this is bad enough, right? But if there was redundancy, so your complementary function already has an x squared e to the 2x term, what would you do in this case? We'd need to multiply the entire thing by the lowest power of x. That would eliminate any redundancy. In fact, I introduced that thought incorrectly. Suppose there were redundancy. Let's say you find the complementary function and one of the solutions, I'll call it y1, is equal to e to the 2x. Well, then we have redundancy with c e to the 2x. So then we'd have to take this entire thing, and instead of yp being that ax squared plus bx plus c, we would need to take this and multiply it by the lowest power of x that clears all the redundancies. So we'd need to multiply all that by x. What I would do is I would just end up distributing it into here, so we'd have ax cubed and so on. What if y1 was x e to the 2x? Then you can see that multiplying by x would not clear the redundancy for cx e to the 2x. So I would have to multiply then by x squared. We'd have ax to the 4th plus bx cubed plus cx squared, right? You don't need to multiply it over here and over here. It's just the entire term needs to be different, linearly independent with whatever you get from the complementary function.